Okay. Hello, everyone. This is Fen Xue from Stanford University. Today, I'm going to talk about the field-free SOT switching with unconventional spin polarization in ultrathin PD-coupled multiple layer. So first part about the background and motivation, and I will focus on about the conventional and unconventional SOT MRAM, and also why we choose AtC SOT MRAM and its application. The previous few talks has already detailed something about the SOT MRAM and also its mechanism, so I will not mention too much here, but I will emphasize a few things that are quite related to my talk today. The bottom few figures show the three types of SOT configurations, type X, Y, and Z, which is defined by the magnetic anisotropy of the free layer. So among them, type X and Z needed the external field to break the symmetry to achieve the determinist switching in a conventional SOT. Next one. Okay. So here I show a schematic and a table about the conventional spin polarization and unconventional spin polarization. So in general, the spin polarization direction, if it's orthogonal to both the charge current direction and the spin current direction, we say it is conventional. And if the spin polarization direction, for example, X and Z, they are parallel to one of the charge current or spin current direction, we say it's unconventional. And the damping-like torque and the field-like torque are expressed like this in the table. With micromagnetic simulation, it shows the time profile of the type X switching. In figure A, it is a conventional type X switching with external field along Z direction to assist the switching. To make it a field-free switching, we need some unconventional X spin polarization. So here I use about 6.5% of that of the conventional spin polarization to achieve the similar speed and with similar switching current in absence of external field. And here why we do type X SOT rather than type Z SOT MRAM. I will explain that in 4 metrics. The first is about the unconventional spin efficiency. So as I put in the table here, it was micromagnetic simulation found that the minimum unconventional spin for field-free type X is much smaller than that needed for the field-free type Z, which is one is 6.5%, the other need over than 26%. And even with the same minimum unconventional spin applied here, if you compare figure B and E, with similar switching current density, type X actually is faster than type Z. This can also be explained by the spin dynamics in the book of Physics of Ferromagnetism by Chikamizumi. So in which he explained that the demagnetization in altiplane direction in the type X can confine the magnetization precession in plane so that it is the anisotropy will stiffer and the magnetization precession trajectory distorted and faster compared to the type Z, which has no demagnetization to confine this magnetization trajectory. And about the areal density, I put a layout here. So you see some MTJ. If compared to type Z, type X just needs some extra space in the X direction, which actually is limited by the F2, which is minimum metal pitch. And it will doesn't allow doesn't need any extra space in this direction. So I will see it is the same areal density as in type Z SOT MRAM. And about the scaling benefit, we have the micromagnetic simulation, and it shows that when the MTJ critical dimension goes down to 30 nanometer, the type X can keep a constant switching current, while type Z need a much higher switching current. So which means the type X, field-free type X can benefit from scaling down. So we are targeting at lower the switching current density for a replacement of SRAM for energy efficient AI computing, and also field-free switching for robust MRAM and edge devices. In the second part, I will present our observations of spin transport in the PD-coupled multiple layer, especially about its joint conventional SOT efficiency and also the current induced switching. The stack is PD cobalt multilayer with 5 repetition, and we vary the cobalt thickness with cobalt and boron in-plane free layer as the layer to exert SOT torques and monitor the SOT efficiency. We did the anomalous Hall effect measurement and angular dependent second harmonic Hall measurement on the Hall bar devices to see the magnetic properties and also extract the spin torque efficiencies of X, Y, and Z spin polarization. So from here, there are 2 important data points. One is at the thick cobalt, which is about 0.4 nanometer. It shows perpendicular magnetic anisotropy. Here, the Y spin polarization, which is conventional, is maximized to 0.33. And the spin polarization also increases as cobalt gets thicker, which is a magnetization dependent behavior. Another data point is at 0.16 nanometer, which is weakly in-plane magnetization. And here we found the maximum X spin polarization efficiency. And and also decreases as cobalt gets thicker. So it is kind of short phasing length and some interfacial effect here. We also use differential planar Hall effect measurement on the Hall bar devices to detect the magnetization switching in the X directions. Figure B is the RH loop and the figure C is the RI loop. And you see that the field-free type X SOT switch is observed in the Hall bar with assistance of unconventional spin polarization along X direction. We also did a micromagnetic simulation to compare type X and the type Y configuration with different ratio of X and Y spin polarization. So with regard to the switching current, the type X SOT MRAM shows about 2 to 3 times benefits compared to the type Y SOT MRAM, especially in the short current pulse regime, which means type X can benefit from scaling down. If you still remember the 2 data points I mentioned in the first slide of this part, SRT1 and SRT2. SRT1 is the weakly in-plane magnetized ferromagnetic state, and SRT2 is a PMA state. And with the 2 samples, we did the X-ray absorption spectral detection at the cobalt L2 and L3 edge using left and right circularly polarized light in a total electron yield mode. And the XMCD signal is calculated as the difference of the XAS signal in positive negative M, and they normalized to the L2 peak intensity. And then the L3 peak intensity will be proportional to the orbital magnetic moment. And we calculate that the orbital magnetic moment per atom in the SRT1 is about 12% larger than that in the SRT2 at room temperature. We also vary the cobalt thickness in the PD cobalt multiple layer. And we see that with the decrease of the cobalt thickness or the cobalt dimension, we obviously see the increasement of the cobalt orbital magnetic moment at the room temperature, which increases the spin orbital coupling strength in low symmetry and thereby generates X spin polarization. This kind of measurement and the calculation for orbital magnetic moment was first measured by Professor Gambadella's group, and they did find with different cobalt dimension spider on the platinum, they find a huge change of the orbital magnetic moment measured at 10 Kelvin. And this time the difference is we measure at the room temperature. So the conclusion is very consistent. Their work was published in Science and Nature in year 2002 and 2003, long time ago. In this part, I will discuss about how to modulate the spin efficiency in our PD cobalt multiple layer. One way is using the magnetic spin Hall effect from the ferromagnetic material cobalt, and the other is the crystalline phase in PD cobalt multiple layer. This is a model with ferromagnetic generated intrinsic spin current with MSHE and MSH, which is magnetic spin anomalous Hall effect. And we can plot the spin Hall conductivity versus the magnetization direction of X, Y, and Z spin polarization. And the orange one is the Y spin polarization, which is conventional, and the green one is the X spin polarization, which is what we investigated before. So here in SRT2, which is the PMA, the MSHE from COBOL, and suppress the MSHE, which is opposite sign, makes enhance the Y spin polarization, which is close to the state of the peak of the sinusoidal here. And in SRT1, which is weakly implant magnetized, the MSHE and the weak defacing in ultrathin cobalt makes unconventional spin polarization. So, which was the magnetization state about near the peak of the green one. Another thing is the crystalline phase in the spin efficient modulation. We did use the 2D XRD to detect the peaks of different multiple layers spotted on the amorphous silicon oxide. Of the SRT2, we did find the one extra peak from the superlattice of PD cobalt, which means it could contribute to the high Y spin polarization efficiency, but probably it doesn't matter with the unconventional spin efficiency. We also try different substrates, different crystalline substrate, like 100 MgO, 110 or 11 MgO, and also amorphous to compare and calculate the X spin polarization efficiency. So we define that the charge current along the 001 direction is preferred for the high unconventional spin efficiency. So which is quite similar to other system that with a high priority of one certain crystalline, it will have generate a high unconventional spin. But fortunately, in our system, even it's on amorphous substrate or not preferred crystalline substrate, it still be able to generate about 0.02 spin unconventional spin Hall efficiency, which is enough for the field-free switching. And this part, I will quickly review the emerging materials for unconventional spins, which are due to low symmetry or other unconventional arrangements. The low symmetry, for example, crystalline symmetry, magnetic symmetry, or chiral symmetry. Like the example from Cornell about the tungsten telluride, it has a SOT efficiency about Z spin polarization about 0.013. And the manganese palladium 3, this work is from our group and it was published this year in Nature Materials for its Z spin polarization. But this material can also be engineered to get a significant X polarization efficiency with about 0.0115, which is also very significant for the field-free switching. And other unconventional arrangements such as the spin splitting effect. For example, the ruthenium oxide material, which is actually also discussed by Dr. Karoubi in the first invited talk in this conference, and also spin-enormous Hall effect, planar Hall effect from the ferromagnetic material, and also interfacial spin scattering. So there are a lot of materials and emerging materials that are supporting the unconventional spin generation. And in the end, I would just conclude that we have demonstrated TAPEX SOT MRAM incorporating unconventional spin polarization is a promising technology with a micromagnetic simulation. We also find in the ultrathin PD cobalt multilayer, their joint unconventional SOT efficiency, which is probably come from the strong optical moment in the low dimensional cobalt. Also, we reviewed some unconventional materials, emerging materials generate unconventional SOTs, and also some other effect that can give rise to spin generation and the modulation. And I would like to acknowledge my collaborators from TSMC and the Lawrence Berkeley National Lab, and also our program funding from TSM and NSF. That's all. Thank you.
Thank you for your talk. Any questions? Please drop any comments in the chat box or raise the hand. Okay, I don't see any question. So could you just quickly comment on for like type X, Y, and Z, different
Oh,
devices? Like, how would you compete? I mean, like compare like the required power for a device and the switching efficiency, like how to determine which
um,
type would be the most ideal to like for making devices.
so actually, I think this configuration is very clear to
Yeah.
see about the mechanism of different type of SOT. So basically, from the latency, type X and Z is much faster than type Y because Y needs some initial precision before switching, and the Y it needs some like the current is high. Even the current density is small need to the switching, but the current is high because the cross section
Right.
along the current channel direction is bigger compared to X and Z. And for Y, it is field free, but we definitely want the high speed in the SOT MRAM. So I think X and Z, they are more compatible. And the Z is in STD MRAM, I think people work on type Z because this is smaller area. So definitely means smaller current. But for SOT MRAM, there's no kind of this problem because current is injected in plane in the inner layer. So then we compare type X and Z, which is faster, which need a smaller current density, and about the fabrication. So I think about the switching current or the speed, I also mentioned in the presentation, which are actually demonstrated in the micromagnetic simulation. But it's right, we need the real device to demonstrate whether type X is really faster than type Z. That's the work we're going to explore in the near future. We're not really demonstrate on the real devices. And about the I think about the switching current or switching current density, that's also from the simulation sees that the similar switching current type S can be faster. So we will see compare them apple to apple if we have the similar stability, which can be faster or which need a smaller current. At least from the simulation, type X is better than type Z. And about the fabrication, yes, type X can have some problem to align the X direction if compared to the type Z, because type Z is just a film normal direction. There is no problem of the X, how the current direction goes, but type X have this problem. So when the in type X, if the current channel cannot align well with the magnetic direction, the anisotropy, then there's some misalignment here, and but it's kind of a type XY structure, which actually is not bad. So we are working on some type X fabrication devices, and we will see whether some good results when it working in nanosecond regime. Yeah.
Right. Yeah. Best of luck for your future work, and thank you for your elaboration.